In this project, various analyses were performed on 3 different iterations of a Tensegrity wing. Each version of the wing was comprised of a wing skin, a spar, and a number of ribs. The first iteration, designated Falcon V4, used 1060 aluminum alloy for all of its parts. The second iteration was an upscaled version of the Falcon V4. Important changes made to this version of the wing included using ABS-PC as the material for the skin and scaling the model up by a factor of 2.5. The final iteration of the model, Falcon V5, involved altering the shape and size of the ribs, as well as increasing the number of them from 3 to 5. For the purposes of this video, the left-hand column will correspond to the Falcon V4 model, the central column will correspond to the upscaled model, and the right-hand column will correspond to the Falcon V5 model. A modal analysis was performed on the skin, the fixed-end rib, a standard rib, and the spar and fixed-end rib together. Curvature-based meshes were used for all of the analyses and no external loads were applied. For the analysis of the skin, the part was fixed at the fuselage end. The element sizes increased with each iteration, while the modal frequencies decreased. The fixed-end rib was fixed at the fuselage end and at the C-shaped hole where the spar would be attached. The frequencies increased with each iteration of the part. The frequencies of the Falcon V5 model were an order of magnitude larger than the Falcon V4 frequencies. For the rib, a fixture was applied to the hole in the rib where the spar would normally pass through. Each new iteration of the model resulted in lower modal frequencies. The spar and fixed-end rib were analyzed attached together as they would be in the completed model of the wing. A fixture was applied at the fuselage end of the fixed rib. The modal frequencies were largest for the upscaled Falcon V4 and smallest for the Falcon V5. This analysis was performed on the entire assembly. Each rib is turned at an enforced angle to achieve a total angle of twist of 10 degrees. The Falcon V4 skin experiences a stress well beyond the yield stress of the 1060 alloy. The upscaled Falcon V4 and Falcon V5 both use ABS-PC as their material and experience significantly less stress. Neither of these iterations experience yielding across the wing skin. This simulation was used to approximate the stress caused by the lift of the wing. It is useful for comparing the closed-form solutions to the analysis performed in SolidWorks. The wing was approximated as a cantilever beam. The dimensions of the Falcon V4 were 20 by 148 by 250 mm. The dimensions of the upscaled Falcon V4 and Falcon V5 were both 50 by 370 by 625 mm. The maximum stress in the Z direction for the Falcon V4 was 14.6 MPa, while the closed-form solution was 11.32 MPa. For the upscaled Falcon V4 and Falcon V5 models, the maximum stress was 3.05 MPa, while the closed-form solution was 3.97 MPa. A compression force of 282 newtons was applied perpendicular to one end of the spar while the other end was fixed. All 3 iterations experienced stresses below their respective yield strengths. In regards to the buckling factor of safety, only one mode was found for each iteration. Of the 3 iterations, only the Falcon V4 experienced a factor of safety below 1 and thus would fail because of buckling. This analysis was limited to only the Falcon V5 model. The fatigue analysis was intended to be performed on the wing skin, rib, and spar of the Falcon V5. However, SolidWorks does not provide SN graphs for plastics because failure for plastics is associated with strain instead of stress. Since the wing skin uses ABS-PC as its material, this analysis could not be performed on it. For the remainder of the video, the left column will correspond to the wing skin, the central column will correspond to the rib, and the right column will correspond to the spar. The parts were each fixed at their frontmost face with a 282 Newton compression force applied normal to the opposite end. The alternating stresses in all locations throughout the model were below the minimum value of the SN curve. The analysis indicated that there was no damage after 500,000 cycles, and therefore there is no need to be concerned with the spar or ribs becoming excessively damaged from repeated usage. Please note that this video did not cover every analysis that was performed as a part of this project. For more information, please see the written report.